Okay, this is the third week for the laboratory. Now, this week's topic is about poles, zeros, zeta, and omega n. We've looked at the P-controller design last week, as far as I remember. Now, this week we will be focusing on poles and zeros and their effects, and especially on zeta and omega n. Now, we've quite a work to do today. We have, for example, a first-order system. And what we're interested in is the following. We will have an interval for omega n. We will change it, and we will look at the step response and how it changes and how the effect of omega n is, basically. Then we will have a second-order transfer function, which is basically the more important one, where we have zeta and omega n. We will look at the different scenarios given here. For example, if we have omega n equals 1, what happens if we vary zeta between 0 and 1? What happens if we vary it between 1 and 2? And then we will also have the omega n effect again here, where zeta is basically constant. And for a certain omega n zeta pair, 0.5 and 0.5, for example, what will happen if we add a third pole that doesn't affect the gain of the system and change the pole's location between 2 and 10 and 0.1 and 0.5. And we will repeat this for the 0. If we add a 0 to this zeta omega n pair, what will happen? How will the step response look like? And then we've also two additional tasks here, which I'm not going to cover in detail because of the fact that we have basically the curve fitting of the settling time and the rise time here for two different versions of the model. I will just briefly cover them because this is especially just additional information and not really our point. So let's begin with the first order system. So let's define omega n, for example, equals 2, and then have gs defined as omega n divided by s plus omega n. Now we want to look at the step response of this system. And of course, since this is a first order system, if we run it, we see that we have this step response here. Of course, we are interested in the variation of omega n, but before we go into that detail, we can see that we have basically no oscillation and no overshoot, therefore. And we know the reason behind this because we know that this has a real pole. And if I'm interested in the solution in the Laplace domain, I can do the following. I can define S and then omega n real. And to find the system in using the similar toolbox, we have basically omega n divided by s plus omega n. Now, in order to acquire the step response here, I'm going to use the inverse Laplace, Laplace command here. And I need to use GSS divided by S. And the reason behind that is the following. We know that the transfer function is defined between the output and the input. So therefore, if I'm interested in the output itself, I need to work my way out here. And what I get is, I get that I need a certain input in the Laplace domain. So if we have a constant, and if it's equal to 1, then we are talking about the unit step function. And the step response is basically the unit step input times GSS and the inverse Laplace of that. Therefore, we have to define US equals basically 1 over S. And that's the reason why I have to divide into S here. And I take the inverse Laplace transform of this in order to obtain Y of t. So if we do that, let's see what the response will be. So we can see now that our response looks like this. We have 1 minus e to the power of minus t times omega n. And depending on the value of omega n, we will have basically an exponential term that decays because we have minus t here. So we can also see that minus omega n here is basically the pole of the transfer function, because this is s plus omega n, so therefore s is minus omega n. And we can also see that, for example, if omega n is equal to 1, then numerically I can conclude that in 5 seconds, if I use x minus 5, this is practically almost 0. So therefore, if I have my 1 minus this term here, then I will get basically 1. And I'm already in the settling time band. So I can conclude that in, for example, 4, let's look at x minus 4, 0.018. Now, if I subtract this from 1, you will see that we will already be in the settling time band. So 2% settling time band, which means that we should enter, if we have a steady state of 1, value of 1, we should enter this interval here and never leave it. So the first time instant this happens, we have basically the settling time. So therefore, we can see that for omega n equals 1, I have already 4. And I know that I'm using settling time equals 4 divided by omega n. I can use this basically. And this is basically because of the fact that it is an exponential term, and that we have yt equals 1 minus e to the power of minus omega n t. So if it's a first order system, it has a real pole, and this real pole determines the settling time here, also the speed of the transients of the system. Now, and due to the fact that this E has minus t in it, and the absolute value of this is equal to 1 at max, this never overshoots. So therefore, we have also this step response here, which has no overshoot at all. It's just decaying, and at the beginning, it's equal to 0 because of the fact that t0 gives here 1, 1 minus 1 is 0. As this time instant increases, this term basically decreases and we achieve 1. So yeah, therefore, we know already that we will have 0 overshoot. And we also know, due to the fact that e to the power of minus t times omega n has a settling time of 4 divided by omega n, we can basically conclude that if we have a certain pole of this first order transfer function, we can go ahead and come up with the settling time before we even use the step function itself, because we know the relation between the settling time and the real pole here. And overshoot is 0. So that's basically it. Now, let's also see what the effect of omega n is. What we have to do is we have to vary it between 0.5 and 2. So let's have 0.5, and let's use 0.5 steps up to 2. So since I have a vector here, I need to use a for loop. For each element of omega n vec, we will define the transfer function gs, and then we need the step response of gs, and then we will use plot here, t comma y. Let's also add some line width. So I want to have a figure on which I'm going to plot this. So hold on, grid on, maybe the X label, time, and then title, maybe step response. So now, course, we forgot to extract the omega n value here. So the ith element of omega n back should give me omega n val. And then I'm going to define my transfer function, use step function, and plot it. Now, of course, we have all the step responses that we are interested in on one figure, but the problem here is that I cannot distinguish between which omega n corresponds to which step response. So maybe I could use some coloring here so that I can visually at least extract one step response and then relate it to the corresponding omega n value. So therefore, what I can do is I can basically choose, for example, a settling time in order to zoom in a little bit. And also what I can do is I can start with a certain color and I can change that color as I'm increasing I, for example, here. So in order to do that, what I can do is I can do the following. I can use the command color here, and I can provide an RGB vector here. So 1, 0, 0, for example, corresponds to red. The red, green, and blue values here. So now if I execute this command, what I can see is I have all in red. Of course, that's not what I'm looking for, but I can change the amount of redness or the color saturation here so that I get a fading effect. Now for that, I can use by the way, the RGB values should be normalized between 0 and 1, not 0 and 255, which you may expect. Now I need to normalize this, so this will be a floating number between 0 and 1, and it will determine how much red will be used in order to generate this color. So therefore, I have already an indicator that can help me out here, which is I. So I starts from a certain value, 1, up to another value length omega n vec. So what I can do is I can normalize this. I have to divide into length omega n vec, and I can use this directly as the color. So I divided by length omega n vec will generate me the color that I'm interested in here. And the more, for example, in this case, red it becomes, the higher omega n value I will get. So this association maybe can help me out in understanding what really happens here. So this is basically the effect. Let's also give a final time of, let's say, 8 seconds here. And there we go. Now I can see that for omega n vec 0.5 or omega n equals 0.5, I will have this behavior here, this almost black color here. And if I have omega n vec equals 2, that means that I will have this bright red step response. So looking at this, I can conclude that, of course, this all the step responses in this interval don't have any overshoot. We've talked about this. That's already set. But I can see that for low omega n values, the system is slower in the transients, and it becomes faster as omega n increases. So there's this inverse relationship between the settling time and omega n, which we already know because it is 4 divided by omega n. But I can also verify this by looking at the step response here. So once I increase omega n, the settling time value becomes lesser because of the fact that it will settle down sooner. So therefore, the system becomes faster. So having a low settling time means that I will have a fast system response. Now, what I can also do is I can also generate another figure and look at the location of the pole. Maybe that's also helping. So what I can do is I can just convert it into a subplot. So let's have 1 by 2 and the first one. And I can also have another one, which will be then the pole zero map or the pole spread in this case. So let's have real values in the x-axis and then imaginary values in the y-axis. Let's have pole spread. Of course, I'm using GCA in order to store the subplots here. So I can provide basically the first argument, which determines on which subplot this will be plotted. Now I need the pool and zeros, or poles in this case. So I'm going to use PZMap here. If you don't provide any output arguments, then the pole zero map will be generated. But I just want to get the poles here. I just want to calculate. So once I have C poles here, I'm going to use the real value of this and then the imaginary value of this in order to plot my poles in here. So, and I'm not changing the line width or coloring in order to get the same effect. So let's run it again. We misspelled this one here. So there we go. Now, we can also see now that this one here has a pole at this position here. And as the color becomes more red, I can see where the pole is. I can also see where the step response or what the step response looks like. But I can also include the origin here because that's not included in here. It is zoomed into this -2 and -0.5 interval. So maybe we want to change the x limits of ax2 such that we have, what was it again, -2. So maybe we may include -2.1 and then 0.1. So you can use x-lim, y-lim in order to determine the x-axis limits or y-axis limits. So it becomes quite handy sometimes. So now I have also the origin in here, but of course this doesn't look like a S-domain representation here, which we can change. So instead of having here hold on, because this is a certain, not the hold on, I'm sorry, the grid on here, we can get rid of that because that will just display this grid in here. We are not really interested in the usual grid. What we can do is we can plot a S-grid here. For those who don't remember S-grid, it uses zeta and omega n values. You can provide zeta and omega n values and it will show you the zeta and omega n, the corresponding grid to the zeta and omega n values. So if you remember my talk about the zeta and omega n parameters, then you might remember that omega n has a certain certain plot to it, and zeta has also. But let's not do it for now because the second task here is actually about that. So we will come back to this here and plot the actual S-grid on top of this plot here. So now, what we've seen from this is that if we change the omega n value, if we increase it, if it's going to the left part or in the S domain, then my system becomes faster and faster, has a faster response. If I'm approaching the origin, then it will become slower. That's also valid. So what we can do is we can also increase this interval a little bit more in order to get a smoother representation here, or even higher, I guess. So there we go. We can see that it's basically gradually fading from this response to this one here. And we can see the movement here. Okay, now this is a first order system which has not that much stuff to it. But if we have a second order system like this, maybe we will get more exciting results and different results. So By the way, let me copy this part here because I'm going to repeat some of it. So again, we will have a figure. We will have the poles and the step responses side by side. I'm not sure about this, so let me comment it out. So the first task is to fix the omega n value to 1. So let's define omega n equals 1, but we will change zeta between 0 and 1. So zeta vec should be between 0 and 1. So since I have a zeta vector, what I'm going to do is I'm going to loop through each element of the zeta vector here, so zeta vec. And I will acquire the zeta value from zeta vec again. Of course, now we don't have omega n val divided by s plus omega n val. Instead, we will have omega n squared divided by s squared plus 2 times zeta times omega n s plus omega n squared. So this is basically a second order transfer function. And then we will have the step response of GS, and then again the coloring strategy here, the poles and zeros, and that's basically it. Now, why do we use such transfer function? In order to study the transients, in order to study how the step response behaves or the system behaves. Well, basically, the polynomial given here in the denominator is a special one. We can use this in order to determine what the poles look like. For example, if we have s squared plus 2 times zeta times omega n times s plus omega n squared, and if we equate it to 0 and try to solve it, we already know what it will look like. Now, in order to look for the solution of this polynomial, we can use the discriminant, which is defined as b squared minus 4 times a times c, which is also, by the way, for as squared plus bs plus c. Now, in terms of zeta and omega n, we know that a is equal to 1. We know that b is basically this here. So let's take the square of that. And minus 4, a is equal to 1, omega n squared. So first, we have to calculate the discriminant in order to assess the type of the poles that we will get. For example, if discriminant is negative, we will get complex conjugate poles. If it's equal to 0, we will have coinciding poles. And if it's a positive value, then we will get 2 distinct real poles. So let's see what the discriminant here becomes. So this is basically 4 times zeta squared omega n squared minus 4 omega n squared. Of course, we have some common terms here. So 4 times omega n squared, and then in parentheses zeta squared minus 1. So from this point, what we can see is we can see the following: 4 times omega n squared will always be positive because we have a square. But zeta squared minus 1 will determine if it's a positive value, if it's 0, or if it's negative. And zeta itself, if it's, for example, greater than 1, if it's exactly equal to 1, or if it's less than 1. So if zeta is positive or greater than 1, then this portion of the discriminant becomes positive, which means that we will have distinct poles, real poles. In this case, it's not distinct. We have real poles that coincide, that are on top of each other. And then we have zeta less than 1, which gives us basically a negative value here. And if we use the square root of the discriminant here, what we can do is basically Or let me write it down like this. We can take this out. This will be 2 times omega n times the square root of zeta squared minus 1. Since zeta is less than 1, this will become negative. So what we can do is we can write it a bit different. We can have minus 1 in here and then another square root, but this time 1 minus zeta squared. So if this is the case, we know what square root minus 1 is. This is basically the complex variable I. So then we will have this here. Now the solution itself will look like this, minus plus, and then the square root here, which is basically this part here, divide by 2. So by the way, this is 2 times. Now, if we divide into 2, these terms will vanish, and this will become our solution. Now, this is the complex conjugate solution here, and we have the real part zeta times omega n, and then the complex part is omega n times square root of 1 minus zeta squared. Now here, if we have zeta equals 1, we can see that this term will vanish, and both of them will become minus zeta times omega n. And for positive values, 2 distinct rules, poles, and for negative 1, this will be basically determining the imaginary part here. So that's basically it here. This is this solution of the poles of this polynomial. Now, if we look at the absolute value of S, we can determine it by using the square of the real part plus the square of the imaginary part here, without I. And then we need to take the square root of this. So that's basically it. Now, if we look, if we expand basically this one here, the squared here, what we will get is we will get zeta squared, omega n squared. So let me write it like this. And then we will also have again omega n squared, and the square root vanishes here. We'll get basically this one here. So if we expand it further, we get this. And now we can see that zeta squared times omega n squared cancels each other out. These terms will cancel each other out. And we are left with omega n squared. Now we had a square root, so omega n squared square root will give us omega n. So what is omega n? Well, basically, it's the absolute value of S here. So this gives us the hint that if we fix this omega n here, then all the solutions will be on a circle. Because if we, for example, say x plus I times y, the absolute value of this is equal to omega n, this will result in the following. The square root of x squared plus y squared, which will then be converted into x squared plus y squared is equal to omega n squared, which is the formula of a circle at the origin with radius omega n. So therefore, if you fix omega n, then we will get circles at the origin. So what happens if we fix basically the argument or the angle of S? Now this is calculated using the inverse tangent or a tan here of the imaginary part, which is this one here, and then divided by the real part, zeta times omega n. So here we can see that omega n is in the numerator, omega n is in the denominator, so they will cancel each other out. And we will be left with the square root of 1 minus zeta squared divided by zeta here. Now, if we have a certain zeta value fixed, a constant value for zeta, then this term here will be fixed. 1 minus zeta squared will be a fixed number, the squared will be a fixed number divided by a fixed number. So this will give me a certain constant value. And the inverse tangent of this constant value gives me a fixed angle. So if we have a fixed angle, then we are talking about a line that it goes through the origin. So now this is important because if we talk about second order systems, then we are talking about a circle with omega n radius and two basically lines that go through the origin with a certain angle. And if they coincide, then we will have our complex conjugate pole pair. And that's basically it. So instead of using the Cartesian coordinates as usual, we are basically using the polar coordinates here, where the absolute value gives us omega n and the angle gives us zeta. So let's run our script, not this one, of course. For the color, we've used omega n vec, which should be zeta vec. So now interesting stuff that happened here. Now, if we zoom in a little bit, we can see that we have an interesting result here. So in order to zoom in automatically, I will use, I guess, 15 seconds of settling time. So let's provide the final time here as 15. Now that's better. And now let me also use this S-grid here because I've talked about the circles and lines. So S-grid here will plot me automatically the grid that I'm interested in. Now I know that my zeta vec will be the zeta values that I have, and I will also have omega n. So let me look for this. So the first argument is the zeta value, and the second argument is omega n. Of course, ax2 should be the axis which I'm going to place this grid on. So now you can see that there's a certain circle with radius equals 1. So that's fixed omega n. And you can also see that we have fixed omega n. It is equal to 1. But we've varied the zeta value. So therefore, we have different angles for different zeta values. For example, 90 degrees for this one here. And if we would have had 0.707, that would be 45 degrees, etc., etc. So, of course, the zeta value itself is related to the angle with the cosine. So if the angle increases, zeta will decrease. So there's also an inverse relation going on here. So therefore, we have higher values if we approach 0 degrees here. If the angle is increasing, then the zeta values are decreasing up to 0. So at exactly 0, we have this perfect oscillation here. So remember or recall that we call the zeta parameter basically the damping coefficient. So if there's no damping, then it will oscillate. So it will be an ideal oscillation. But if we have a certain zeta value, depending on the magnitude of the zeta value, the oscillations will basically vanish. So we have some oscillations here, some peak values here, but they will eventually be basically damped out. So therefore, if you have a certain omega n value, we're basically on the S domain on a circle with the radius of omega n, and we can decide on the zeta value that will directly correlate with the transient behavior of the system. So if you want to have a certain overshoot, for example, what you can do is you can basically choose your zeta value. But of course, we've seen that last week, the real part of this dominant pole pair or the complex conjugate pole pair here, determines the settling time. So if we have, for example, 0.8 here, then we will get 4 divided by 0.8 as the settling time. Now, if we use a different zeta value, a lesser one, then the settling time will increase. I can directly see that from this S domain here. If I want to have a fast response, then I should probably choose this one here, which has 0 overshoot, which is critically damped, and will have 4 seconds of settling time because of my formula. So therefore, if we look at the S domain, and if we're talking about zeta and omega n value pairs, then we're talking about the transients of the step response of the transfer function that we want to choose. So there's this mapping between the poles of a second order transfer function and the behavior of the step response. So this is the crucial part here. Now, of course, we can also have zeta values higher than 1. So in order to examine that case, I'm going to copy this, maybe the whole thing, and have another plot where the only thing that changes will be basically the zeta bounds. So again, omega n is equal to 1. Again, we have a zeta vector, and everything will be repeated, but the bounds are changed. So let's see what we get. So now on the left here, we have again fixed omega n, but then the zeta values change and we have these step responses here. But when zeta is greater than 1, you can see that one of the poles will approach the minus infinity, or they will tend to the left, but the other pole will tend to the right. It will approach the origin here. At exact zeta equals 1, we are again on the circle of omega n, but then we deviate. We are not on the circle anymore. And since we have basically zeta greater than 1, all the angles are basically 0 degrees. So interestingly, we have lost the zeta information here. Not directly, but it's not linear anymore. We cannot directly determine if it's going to be somewhere on the circle because it's not on the circle anymore. So basically, the step responses here, since all of the poles are on the real axis, the step responses don't overshoot. They don't have any oscillation in them. The only thing that changes here is basically the settling time. And we can also see that one of the poles here is approaching the origin, and they will be basically determining the speed of the transients. Because the other one goes to the left, and if you recall, if you go to the left on the S domain, if the magnitude of omega n increases, then the system response becomes faster. But these are basically two real systems in cascade connection. So one of the input is basically the output of the other pole. So if we have, for example, 1 and 2, what we have in the denominator, or what we have as the transfer functions, would look like this, 1 divided by s plus 2. So one of them is faster and one of them is basically slower, but the overall speed will be dominated by the slower one. Because if you have, for example, your cell phone and then you have the internet connection, both of their speeds will determine your overall speed because they're dependent on each other. So therefore, we have this case where we call this overdamped, where the damping is a bit too much, and one of the poles becomes fairly slow and the other one becomes really fast. So their interconnection gives us basically slower responses here, as you can see here, because at this point we have a lesser settling time, a faster response, but as it increases, it will become slower and slower. That's the reason why we most of the time don't choose overdamped systems, because they will become slower. So they are not a good candidate for controller synthesis. But we like to use these ones if we are okay with a certain overshoot. And we can determine the settling time, the rise time, peak time. They have all the formulas for this. So therefore, what we tried to do last week was to come up with a p-type controller in order to have a certain settling time. And we've changed also that settling time. And the design method was to determine a zeta and omega n value pair. If you know what zeta and omega n should be, then you're good to go, because you know what the settling time, the overshoot, all the transient properties will be. But of course, I've talked about this, overdamped systems, where systems have greater magnitudes than 1 for zeta, are not really the ones that we chose most of the time. It's not directly too bad to use overdamped systems, but we don't have any formula to determine how fast the system will respond, what the settling time would be. So therefore, it's basically more a trial and error kind of approach for overdamped systems for now. But here we have formulas, and we can predetermine what the poles should look like if we want to have a certain requirement satisfied for settling time and overshoot. So that's basically what I'm trying to explain here. So this is the most important case that we should analyze, because we will use most of the time zeta and omega n value pairs in order to determine the transfer function that we need. So let's see what we have. Now we have C here, where we change omega n and fix zeta. So let's quickly do that. Let me comment it out here. So here we have, for example, zeta equals, what was it again? 0.5. So let's take 0.5 here. Now let's change omega n between 0.5 and 4. 0.5 and 4. Now, of course, I have to change all the places where zeta vec is present. So we're taking omega n out of omega n vec. And we know what zeta is, so therefore we're good to go. Let me get rid of the settling, the final time here. Use omega n vec here. So we have zeta, a fixed value, but omega n vec is a vec. So therefore, now we should be good to go. So let me also repeat this for the second case where zeta is equal to 1. Figure 2, change it to 1. So now it seems like the omega n steps are a bit too fine. So there we go. Again, 15 seconds of a final time is also good. So let's also do that. There we go. Now, here we have zeta equals 1. Here we have zeta equals 0.5. And we can see the omega n circles here, also here. Now, here we have the y limit 10 to the power of -8. So this means that it's numerically unstable at this point. So we can change the interval of this and also maybe of this. So let's quickly do that. Here we need to look at the y limit of ax2 between -1 and 1. Let's have x limit of ax2 between -4.1 and 4.1. There we go. That's much better, I guess. yeah, we are good to go. Now, we can see, for example, that for zeta equals 0.5, we have this certain line, which has a certain angle, and all the omega n circles are coinciding at these exact points here. So we have omega n varying, but the zeta is basically on a fixed line. And we can also see from the step responses that the peak values are also aligned. So the maximum values are basically fixed here. Which brings us to the next point, which is that if we have a fixed zeta value, then we have a fixed overshoot. And that's it. So the zeta value determines what the overshoot looks like. Now, in this case, zeta is equal to 1, so there's no overshoot. And if we increase omega n, we can again see that the system response becomes faster. That's also interestingly the case for the left one here, but the reasoning is not exactly that omega n is increasing, but the real values are also moving to the left. So if we have the settling timelines for each setup here, then we can see that the real value is basically increasing. And if that's increasing, 4 divided by the real value will decrease, so therefore we will get faster responses here. So now we've covered the first order system and a general second order all-pole system up to this point. So let us take a little break, and after the break we will continue with adding a pole and adding a zero, and we will continue our discussion on that. Okay. Yok tabii ki gelebilirsiniz yani. Problem mi? Okay, now let's continue on our discussion today. Now, up to this point, we have looked at first order systems where we change omega n. We've seen that first order systems do not overshoot. And if the magnitude of omega n increases, settling time decreases, therefore the system becomes faster. For second order systems, we've talked about that. If we have a fixed omega n, we're talking about a circle with the radius omega n. And then if we choose some zeta values, we will then basically end up in a complex conjugate setup. Now, let's see what happens if we add a pole or a zero to the system. We need this because last week we've designed a p-type controller for a third order system, and I've talked about the fact that we have only settling time formulas or overshoot formulas for second order all pole systems. But we've also accomplished to design a p-type controller for a third order system. And the basic fact for this was that if we add a pole in the non-dominant region, then we would be able to use the formulas again, since it would behave like a second order system. So basically, adding a pole and adding a zero is constructed to analyze this and see what really happens here. So let's define our system. Where zeta is 0.5, omega n is 0.5. Therefore, we will have a second order part where we have the transfer function omega n squared divided by 2 times zeta times omega n, and then omega n squared again. So this is the second order part. We will have 2 poles, and that's it basically. Now we will have a p-vac here, and the values vary between 2 and 10. So let's have this. Now again, we will take each value from this vector here, and then construct the third order transfer function, apply step, and see how that will affect the whole system. So let me copy this part here. And then this part here. So now each element of pvec, where p is equal to the ith element of pvec. Now, instead of doing this, we will have p divided by s plus p times the second order part here. Now, again, pvec and pvec. So for zeta equals 1, let's have pvec for the S grid. That should be basically it, I guess. So let's run it. Now there's the second case. Let's also duplicate this code. And the interval for this was 0.1, 0.5, 0.1, and 0.5. There we go. Of course, I didn't update this. So there we go. Now, on the left, we have added our pole between 2 and 10, which we can see from these omega n circles here. And we can see that the step responses are much alike. So they are not really that different in terms of transient properties. For example, they have almost the same peak. They have almost the same settling time. The rise time seems to be intact. So if we have a certain distance between the pole, the third pole that we've added here, and the dominant real value, then we can see that the dominant pole placement converts the behavior to a second order system's behavior. And the dominating poles are these poles here. So therefore, we can conclude that this system behaves like the second order system without the third pole here. Now, this is not the case if we have the real values not that distant. For example, if they are in the vicinity of the real values of the dominant ones, or the supposed dominant ones, then we can see that the behavior changes in terms of overshoot, in terms of rise time, in terms of settling time. So everything is different. Therefore, if we have a pole in the dominant region, then our settling time, overshoot, rise time formulas do not apply. If they're distant, if they're further away, then we have a good system that we can basically determine the transients of. So therefore, last week we've designed a p-type controller, and it worked for the same reason as in here. So if we have a dominant pole placement, if the third pole is further away, then the transients are alike. So the transients can be determined by the second order formulas. Now, if we achieve a dominant pole placement like this, then we can use our settling time. If not, then we have different transient results here. So this tells us the following. If we are trying to design a controller and we decide to use dominant pole placement, the thing that we do is we try to assign the two poles according to the formulas, and we check for the third pole. If it's distant enough, then we can see that it will work. If not, then we have to update stuff. For example, we need to, update the transient requirements. For example, if we have a settling time, then we may decrease that because the pole is here, so the pole should be placed closer to the j omega axis or the origin, because we need a certain dominance here. Therefore, a backup plan here would be that if you design a controller and it's not dominant, then you should, for example, increase the settling time. Have a smaller closed loop requirement. So therefore, hopefully, you will end up in a more dominant pole placement strategy. Now we can see the effect of the poles here. So what happens if we add a 0 instead of a pole? So let's examine that. So I copied and pasted the same thing, but now instead of having pvac, I will have zvac here. And we're not plotting the zeros. Let's plot them. Let's use circles. And again, we have zvac. So let me copy this one here. There we go. So what else? Of course, we have to change the transfer function here. Instead of having z divided by s plus z, we have to use s plus z divided by z. So let me copy this one here and paste it in here. So we're basically choosing a value from this vector based on I, the ith element here. We're adding s plus z divided by z to the transfer function. So we have a second order system with a 0. And then we have the step response and the pole 0 map. Let's see. Now again, on the left, we have the dominant pole placement strategy where the two poles, according to the settling time formula, for example, are chosen. And then we have a 0 that's again further away to the left. And the transients are again almost the same. The rise time, the overshoot, the settling time, the step responses even look alike. But in the dominance region, if we have a 0 in the dominant region, that's not the case. And even worse, we have 3 times the overshoot, or we have 300% overshoot, more than 300. And again, the transients do not look alike. Therefore, we cannot conclude that this system would work like expected. Now, it's even worse to have a 0 in the dominant region than having a pole. And the interesting thing about this is the following. If we have a system that has a 0 on its own, naturally, then there's not that much that we can do because it has a 0 at that point, and we have to live with it. The best we can do is choose, again, the real value of our dominant poles such that there is a dominant placement strategy. So having, again, a slower settling time requirement or rise time requirement would hopefully solve the issue. But if the 0 that appears in the closed loop is added by the controller itself, now that's on our fault. So if we have a 0 in the dominance region and that 0 belongs to the controller, then the designer has to fix it because it's not appearing naturally. You're adding it. So the response would be then added somewhere else, added so that it has a dominant pole placement. So therefore, we have to be careful with the controller zeros. Now, we have covered only p-type controllers, therefore that's not an issue up to this point, but at a certain point, we will use PI controllers or PD controllers, which have zeros in them, and they will appear in the closed loop. So therefore, we have to be careful about the zeros of those controllers. Because if they're in the dominant region, then, for example, your overshoot requirement will be violated here, or the settling time would not be the same. So therefore, and think about the following, if you have a higher order system, like a 5th order system with 3 zeros, then it's really hard to come up with a controller that has this dominant pole placement strategy. So therefore, control of low order systems may be simple, but as the degree increases of the open loop or the plant, then the difficulty will also be increasing, because you will have much more poles or zeros to keep away from the dominant poles here. We have only one here. It may be the case that 3 poles should be placed in the non-dominant region. And of course, if you know anything about the root locus, you would see that a p-type controller has not that much power. So you cannot keep all the poles away with a p-type controller. So that will bring us to the next week's discussion probably, where we will talk hopefully about the PD-type controllers or PI-type controllers. Now at this point, the only thing or the important conclusion is to try to keep all the poles and zeros other than the dominant ones away from the dominant ones. So lastly, we have these formulas here. Of course, I'm not going to explain them in much detail. We will look over them because of the fact that it's not really our point of discussion, but I've added them for additional information. So we know that the settling time for a second order system, for example, is 4 divided by zeta omega n, but the question is, can we obtain it ourselves or can we verify it ourselves? And it's possible. I have, for example, varied the p-value here or the z value here, or we can change, for example, zeta or omega n. So why not change both zeta and omega n in an interval and look for all the settling times and then try to come up with this formula or the coefficient of this formula. So it's possible, and we will see how. And the same applies for the rise time. We again have some rise time formula. Can we obtain the coefficients of this, or can we model the rise time of systems with this formula? So in the PDF, I have provided pretty much everything that I've talked about today. I have forgotten to talk about the impulse response, but it's not really that big of a deal. So we can see the omega n lines. If omega n is fixed for some values, you can see that this will be the placing strategy here. And the corresponding step response is again colored with the tone of red. Now, then we've talked about varying omega n with certain fixed zeta values. This is from the previous one, I guess. Oh no, this is the one. We have fixed omega n. So this is basically one of the intervals. This is a bit mixed up, but yeah. We have fixed omega n, we have zeta intervals. They correspond to these ones here because we have omega n equals 1. This is the radius, and then we have different zeta values, and they will correspond to different behaviors here. And the same applies for zeta between 1 and 2, but we've talked about this, that if zeta is greater than 1, it really doesn't have that much applicability. Yani şu an için yazmadım ama 3 boyutludan kastın. Yani bir ara yapabiliriz onu. Bir ara şey yapabiliriz, bakabiliriz ona. Then we have talked about changing omega n with fixed zeta, where this is 1. If zeta is 0.5, again, we have the same peak values, which also means that the zeta value corresponds to the overshoot behavior. And then we've tried to fix zeta and omega n and try to add a third pole. Now, here exactly, we have the zeta and omega n values, and with the dominant poles here. Then we are changing the added pole, its position from -2 to -10, and then we can see that they share the transient behavior. Therefore, we can apply the formulas for all the systems with these third poles here, for these 2 poles. Now, if they are in the dominance region, then we can see that, for example, it behaves like an overdamped or an underdamped system. But in reality, we have 3 poles. Therefore, it's not really the case. And we cannot really apply the formulas that we have as tools. The same applies for adding 0. We've seen that it has much more effect on the overshoot. But overall, again, we cannot really use our formulas for such systems. Then, if we want to, for example, model the settling time of a transfer function, then we can use the following. We have, for example, a grid of zeta and omega n values. So this should be the whole S-plane, the left half plane. But we have a limited region here. And for each point in this region, what we do is we calculate, this is for the first order system, for example, for each omega n value, we take the omega n value, we use step info in order to acquire the settling time. So this is the experimental settling time, and we store this as a table with omega n and settling time values because our formula is depending on omega n and only omega n. And then the fit type function from the curve fitting toolbox has a notation as follows, where you give the mathematical expression here. It is a divided by x, and then we have the coefficient. We want to determine what a looks like, but the result will be stored as z, which is the dependent value, and the independent value is x, which means that x will be changed in a certain interval, or the input is x, the output is z, and the coefficient is a. So in this case, we use the fit function here. We give it the corresponding columns where omega n values is the first one and ts values are the second one. And then we get the, we give the additional information about the curve fitting problem. And then we have a starting point of 0, which means that a will be tried with 0. So you can also skip the fit type function and the fit function here, but it's not really that important in this case. So once this is done, we get the first order expression here with a coefficient that was calculated by the function fit. Now, again, it is also possible to define this region in the S domain. And for each omega n and zeta value pair, we can calculate the settling time using, again, the step info command and store this in a table, and then feed this table into the fit function here in order to get the following results. For example, for a first order system, 3.9121 is the coefficient that was calculated by the fit function. For a second order system, this is a bit different, 3.7972. So, of course, theoretically, we should have a infinitely large and a very fine grid here, but that's not possible. So a numerical approximation is the only way. So we can also use the rise time for this, and then we can see that it is possible to calculate the coefficients of this. By the way, this is not a linear fitting problem if you look at it like divided by zeta times omega n, but what you can do is you can approximate this by defining a new variable that is corresponding to 1 divided by zeta omega n, because we're only changing omega n in this case. So that was what I basically coded here. Again, here if we do... Tabii.
Yerleşme zamanları ile ilgili formüller burada yazmış ya. Peki biz teorik olarak mesela aynı zeta, ya da şöyle söyleyeyim, aynı zeta için birinci derece, yani şunu demeye çalışıyorum. Reel kısmı aynı olan tek kutbun mu daha hızlı oturmasını bekleriz, yoksa atıyorum aynı reel kısım artı eksi j omega olan iki kutuplu bir sistemin mi daha hızlı oturmasını bekleriz?
Şimdi şöyle, settling time açısından diyorsun. Bir elinde çift olsun. İmajiner kısımlı olan mı hızlı davranır, yoksa birinci dereceden bir sistem tanımladığım reelde o mu daha hızlı davranır diye soruyorsun.
Evet, onu demeye çalışıyorum.
Şimdi settling time'ı sonuç itibariyle aynıysa aynı saniyede %2'lik banda girmesi lazım. Yani bu imajiner kısımla alakalı değil, reel kısımla alakalı zaten. Şimdi şeyin Ogata'nın kitabına bakarsan veya konsol textbooklarına bakarsan orada aslında settling time'ın tamamen reel kısımla alakalı olduğunu göreceksin. Çünkü sinüzoidal terim geliyor ters Laplace'tan. Çarpı e üzeri eksi zeta omega n t geliyor. Şimdi zaten o e üzeri eksi zeta omega n t'nin zarfı içinde kaldığı için tüm cevaplar sinüzoidal kısımlar olsun olmasın. E üzeri eksi zeta omega n t üzerinden settling time formülü çıkarıyorlar ki o da 5 tau veya 4 tau gibi bizim e'nin 0.18'e inme süresi. Yani tamamen oradan geldiği için ikisi arasında fark olmaz. Eğer reel kısım zeta çarpı omega n olarak aynıysa, yani hem birinci dereceden zeta omega n işte 1'e eşit olsun mesela, hem birinci dereceden sisteminki 1, hem de kompleks konjügette 1 artı eksi j olsun, ikisinin de settling time'ı aynı olmalı. Ama burada kısıt tabii zeta üzerinden geliyor. Çünkü zeta'nın 0 ve 0.7 aralığında mıydı? Tam emin değilim. O aralıkta bu setting time formülü çok daha doğru sonuçlar veriyor. Mesela zeta eşittir 1 için bu formülü kullanmamak gerekiyor aslında. Dolayısıyla imajiner kısım aslında daha çok overshoot'la alakalı. Ama setting time'ı bir kutup çiftinin veya kutbun reel kısmı belirler. Yani aynı olmalı mantıken. Eğer doğruysa formül. Then what we can do is we can basically use zeta divided by omega n as a variable and also 1 divided by omega n as another variable. In that case, if you change or substitute these expressions into new variables, then you have a linear fitting problem. So that's the reason why I have defined a times x divided by y plus b divided by y. If you want to do this manually, you can basically define zeta divided by omega n, like x1 and x2 is 1 divided by omega n. So, and then we've used fit type here in order to come up with the second or first order approximation of the rise time formula here. This is just to show you that you can also work your way out using numerical tools. If you have MATLAB, you can just go ahead and try to find it yourself. But of course, it is also worth mentioning that you should check out the textbooks. The Ogata, Kuo, and Nise books are very, very extensive in these topics here. Or maybe your lecture notes, you should check them out in order to get more information or detailed information about these. So that's basically it for this week. And from next week on, we will be designing more complex controllers, and we will look at the design problem here. But mostly we will stick with the dominant pole placement for quite some time. And the reason behind that is that we have certain formulas, and we will try to apply this for higher order systems or systems with poles and zeros. That will be a challenge because of the fact that dominancy would be, again, a question of the controller choice or the question of requirement choice, because that will affect the dominance. And hopefully we will talk about that. So that's it for this week. If you have any questions, I'll try my best to explain them. If not, we will see you in the next lesson.